The primary objective of this project was to incorporate ideas and fundamentals through our years of study at Clemson University. In this project, we exercise our understanding of signal systems and transforms, electronics, power systems, computer vision through facial recognition, microcontroller interfacing, and more. We combine these fundamentals into a project that could see practical use cases in real life to show how our education has prepared us for each of our next steps. Our group's main motivation behind this project is that many of us experience early stages of tinnitus, also known as hearing damage. It is a common trend for those with tinnitus to unknowingly listen to media, being television, movies, or music, at volumes louder than someone without the condition wants to hear it. Our project leverages the non-scattering nature of high-frequency acoustic waves to target sound waves at people. This sound is transmitted at a frequency that humans cannot hear, and only when the waves demodulate at their destination, the sounds are audible. The idea is similar to whispering in someone's ear. Surrounding people can still hear what's being said at a lower volume, or not at all. Our implementation is 14 parallel ultrasonic transducers that transmit a carrier wave that is not audible until the acoustic wave demodulates on the surface it hits, at which point it is audible. We use a camera in junction with a Raspberry Pi 4 to run Python facial recognition using OpenCV to grab a frame from the camera. Once every 8 frames, the image is processed and scanned for faces. The face with the lowest index will be chosen to be followed using our 2-axis servo setup. The face library can be cleared by pressing K on the keyboard in order to allow for a new face to be the lowest indexed. Although we don't take advantage of it in this project, this library is very powerful and can actually recognize different pictures of your face from different time periods. Here is an example of me pressing the letter K on the keyboard to reset the face dictionary. As you can see, my face increases in index. The servos used to control where the camera and array are pointing are controlled using the Pi's GPIO pins. We change the servo's angles once every 8 frames and do so in very small steps. We found out that in many instances our servos would overshoot when trying to center the face on camera, resulting in a sort of jitter, never allowing for the face to be centered in the frame. The task of producing an audible directional audio signal is one of analog circuitry design. This system is in 2 phases. The circuitry must first modulate an audio signal into a pulse width modulated ultrasonic carrier signal in which the duty cycle increases with the input voltage. Next, it must amplify this signal to be sent to the speakers. The modulation works by configuring a 555 timer to produce an astable PWM signal. An amplification is done using an L293ID IC, chosen for the desirable high-frequency response of its H-bridge design. The hardware team is responsible for the development of a physical structure to support the system. This includes installing and powering servo motors that can be driven by the Raspberry Pi to aim speakers. MG996R servos are chosen due to their torque characteristics at 5-volt operation, and a 3D printed structure is used to mount the camera, speakers, and the servos. For the speakers themselves, we use CT40-16 transducers, chosen for the frequency response and operation voltage characteristics, which can reach 40 kHz and 36 volts RMS. Observing different parts of the analog circuitry individually reveals more detail on the functionality of the system. Here, the yellow plot measures a test sinusoidal input audio signal to the modulation circuit, and the blue plot measures the result of the modulation. The effect of the input signal on the duty cycle is evident. In this image, the results of amplification are shown. The yellow plot measures a modulated signal going into the amplifier, and the blue plot measures the amplified signal. As can be seen in the vertical measurements shown, the amplifier produces a roughly 3.8 times voltage increase in our configuration, enough to power the speakers. In summary, we have a functional device that completes our set goal and follows the project-planned flowchart. While there are improvements that could be made, this design is a fully functional proof of concept. If we were to take this to market, we would need some finer tuning and minor design changes, but as a whole, our group has completed our project sufficiently. Some future directions we could take the project in could be finer tuning of sound quality and volume enhancement. We could also research and implement better array shapes that would result in less acoustic scattering. On the computer side of things, a stronger computer would allow for higher speed tracking. This would result in less jitter in camera movement and more precise aiming.